Today we're going to be talking about normal distributions again, but this time breaking it down into the PDF, or probability density function, and the CDF, or the cumulative distribution function. All right, so here's the roadmap for today. We're going to talk about frequency charts, which we've been doing before, and then contrast it to this new idea, but still fairly elementary, of cumulative frequency charts. Then we're going to do a very brief and broad review of calculus. It's going to be a very elementary review. No actual calculations, just conceptual. And then we're going to talk more deeply about the probability density function and the cumulative distribution function. You have to sort of reprogram yourself to see PDF and not think of it as a portable document format. All right, let's talk about frequency versus cumulative frequency. So far, what we've been doing is we have some sort of variable, such as a score on the SAT verbal, and we have all these values that that variable can potentially hold. And we've been talking about what percentage of our sample or population have achieved that score. So 1% score 800, 3% score 750, right? And so that's been what we've been talking about so far. Now here, when I write percentage, I'm really talking about relative frequency. But it's largely the same thing as frequency, so not a big deal. Now, when we talk about cumulative percentile, what we're really talking about is not just not just the people who have achieved that value, but an accumulation of everybody who has come before it. So let's start off at the bottom. So here, only 1% of the population has achieved 250 points. I think that's like one of the minimum or something. But 3% have achieved 300 or below. Right? So if you're in the third percentile, you have outperformed 3% of everybody else who's taken the test, right? Not something to write home about yet. So this 7% actually accounts for this 4% as well, plus a little bit extra. This 3% as well, plus a little bit extra. And the 16% encapsulates everybody who's come before it. Now, cumulative percentile is really helpful if you want to know your ranking in a performance. For instance, you want to know what percentile of the population you're in. You don't just want to know that 1% of everybody who's around you has also achieved that score. You want to know how many people have you outperformed. Cumulative percentile, by continuously adding all the people up that have come before you, it gives you that ranking. So when you get to, if you're in the 95th percentile, you know you've outperformed 95% of that, outperformed or equally performed 95% of that sample. And so that's why cumulative frequency is really helpful to us. But one of the things you want to notice is that cumulative frequency, when you just look at the number right away, you don't know how common that score is. So when you look at 98%, you don't know how common 750 as a score is. But you could easily find that out just by looking at the difference between 98 and whatever cumulative frequency came before it. So that difference is 3. And so 3% of people have been in that bracket. Now, another thing about cumulative frequency I want you to notice is that it's a monotonic increase. It means that there's no going up and then going down and then going back up and going back down. So there's no changes in direction. It's continuously going up and up and up and up. And that makes sense because you have to add up everybody who's come before you. All right, so that's cumulative frequency. And when you look at it on a visualization, now you could see what I mean by monotonic increase. So here we have an example of monotonic increase. This curve goes up and up and up and up because it's adding up everybody who's come before you. So you have to be at least the score before you or higher, right? And so every score is improving on the previous score. Whereas before in frequency, we could have non-monotonic curves, because here you could go up, you could go down, we could have a uniform distribution, we could have all kinds of things. But in cumulative frequency distribution, you can't have a you can have a uniform distribution. If everybody has only received the bottommost score, then you would have a uniform distribution because you'd be adding 0 every time. But otherwise, the most frequent shape that you'll see is a monotonic increase that looks like this. Here we see just this like normal-ish looking distribution, and what ends up happening when you have this normal-ish distribution, you have this sort of S-shaped curve when you transform it into cumulative frequency. Because this part in the middle, right here, sort of here, that part corresponds from about 400 to 600, right? So that part corresponds to the sort of biggest jumps. And as you see, there's big jumps here too, but the jumps are just going in one direction. All right, so that's how it looks. Now, let's put that on hold for a second and talk about calculus in brief. Now, a lot of people, when they think about calculus, they think immediately derivatives and integrals, like integrating stuff, getting derivatives of equations, right? That's sort of what they think about. But let's think about it, let's step back and think about it conceptually. Calculus, in some way, you could think of all equations as being on a continuum. And let's just say there's some equation that we're thinking of, y equals x squared, or something like that, right? So we all know what that function looks like. It looks something like this, a parabola. And when we think about this, we're saying, okay, this is just plotting exactly what y is given some x, right? And that's all that graph is. So when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 4, right? And so we're just plotting those precise points. Now, when you go and take the integral, I'm going to put the integral on this side, integral, versus you go and take the derivative, you're actually describing now two sort of different aspects of the same graph, but in a graph. So when you talk about the integral, now what you're doing is you're no longer plotting these particular points, but now you're plotting these areas. So when you think about integral, think about area, right? And so whenever you have some sort of curve or some sort of shape or line, when you take the integral, you're really going towards getting the area. And you could get these areas of these weird, bizarro shapes. And at this same time, if you go on the other side of the continuum and you go towards the derivative, what you end up getting is not the area, not like sort of flushing out the shape, but instead, you're just getting the slope, right? So here, instead of actually being interested in the points themselves, now you're interested in these little slopes, right? It's sort of hard to see, but all these little slopes at every single tiny point, right? And you're really graphing those slopes. And so you're really interested in these changes, right? So here, I want you to think slope. And obviously for any equation, so even when you get a graph of slopes, you could get the slope of slopes. And then even when you have the slope of slopes, you could get the slope of slopes, right? So you could go more and more and more towards that derivative side. Or on the other hand, if you get an area, a graph of a whole bunch of areas, you could get the areas of that curve, right? And then get the areas of that curve, right? So you could go more and more and more towards the integral side as well. Now, this is going to be important to us because we're going to be interested particularly in a curve that looks like this, the normal curve, right? The PDF. And what we want to do is get the cumulative areas of that one, right? And so which direction should we go? Well, we should probably go towards the integral direction. Because what we really want is the cumulative areas of this function. And so that's going to be an important concept. All right, so now let's talk about the PDF, or what we call the probability density function. Now, we've talked about how the standard normal distribution is a little bit different than just a normal distribution because the mean is 0 and the standard deviation is always 1. And because of that, it's sort of a special case that is very, very helpful to us. And so there's a special sign we use just for the PDF of the standard normal distribution. And that's what we call little phi. And it looks sort of like this. When it's written out, sometimes it looks like a lowercase y, right? So that's how people sometimes write it. So that's what it looks like. And that's the symbol we use to denote that we're going to be talking about the standard normal distribution. So the function actually looks something like this. So x, it just represents, some value on your variable of interest, right? And there's a couple of different ways you could write this, but the crux, the heart of this is really e to the negative 1/2 x squared. That's sort of the heart of this, and even this 1/2 is sort of like, it's just a constant. I just really remember it as e to the negative x squared. Like that's the heart of this function. That's the heart of the shape, all divided by 2 pi. And obviously this could be written in slightly different ways. You might also see it as 1 over square root of 2 pi, and then you multiply that to the exponential function to the power negative 1/2 x squared, or x squared over negative x squared over 2, right? So there's a couple of different ways you could write that. Now this function, it might seem a little bit crazy to us, but let's break it down. You might want to use wolframalpha.com, or if you have a graphing calculator, feel free to use that. That'll work largely in the same way. So if you go to Google, wolframalpha.com is sort of like a combination fancy graphing calculator / Wikipedia for math and science stuff. So it's quite helpful. And it's free. All right, so here we could write any function we want. Let's start off with just, I usually just put in y, just because I'm used to that. Y equals e to the negative 1/2, I'm just going to write 0.5 x squared. So let's just start with that part first, and let's see what we get. What Wolfram Alpha will do is it'll actually draw the equation for us. So notice that already we have something that looks like a normal distribution. But one of the issues is we just want to divide it by the square root of 2 times pi. And that will just change the shape of it very slightly. But notice that, largely it's the same basic fundamental shape. You divide by that constant to give you a couple of properties of the normal distribution that are going to be important to us later. But really, the heart of this function really is that exponential function. And it's in particular exponential function to the x squared power. That's what really gives us that nice curve. All right, so that's what we think of as little phi, and that's this equation. Now, the PDF for the normal distribution, now that we know has any kind of mean and any kind of standard deviation. One thing that I forgot to point out is that when you look at this, I'll make it smaller here. All right, so when you look at this, one thing that you'll notice is that the mean, or the point of symmetry, is 0, right? So it's right there. And one standard deviation out, if you go about one standard deviation out, that looks about like 68% of that curve, right? It seems like more than half, right? So this really depicts the mean being 0 and standard deviation being 1. Now, if we wanted a regular old normal distribution that didn't have a mean of 0 and that didn't have a standard deviation of 1, what would the equation, what would the formula for that be? What would the function for that be? Well, the general equation for the PDF, we don't have a special symbol for it. We just use the regular old symbol that we use for all functions, f of x. And here, it's still this function at the heart of it. But all that we're doing is we're going to be adding in mean and standard deviation as variables so that you could put in whatever mean and standard deviation that you want. So let's start with the heart part. So it's e to the negative, and it's still e to the negative. But instead of 1/2, we need to change that x squared function. It's got to be x minus mu, because we've got to put in that mu. If mu is 50, we want that point of symmetry to be over 50. If mu is -5, we want that point of symmetry to be over -5. And then we want to square that. So we're really squaring that distance. Here, we've done that actually, except it's x minus 0 all squared, right? So that's why we could just condense it as x squared. And then all over 2 sigma squared. 2 times sigma squared. So that's where that 1/2 comes from. And when sigma is 1, it's just -1/2, right? So, so that's why you don't see that crazy part in here. And then all divided by, and there's just one more thing, 2 pi sigma squared, right? And so another way you could think about it is having 1 over sigma, right, times phi, except instead of just putting in x, we're putting in x minus mu over sigma. So if you put this function in here and you substitute x with all of this crap, right, then, and you multiply by 1 over sigma, then you would get this equation. This is the simplified version, right? And so now let's put this into Wolfram alpha, and let's see what we want. Let's see what kind of function we have. So we could put in, let's say, a mu of, oh, sorry about all this. We could put in a mu of, let's say, 550 and a sigma of 100, right? And